Hello, everyone. Thank you all for sticking around after 2 full days. It's almost over. Today, I'm going to speak of Uber's efforts in building a web-based visualization platform for self-driving cars. Just an overview, I will talk about how data visualization is making an impact at Uber. I will show you the kind of data that autonomous vehicles are generating and how we make sense of them visually. And finally, you will see how you can create your own data visualizations using the open source frameworks that we created or improved during the course of this project. My name is Xiaoji. You can call me Miss X. I am a software engineer at Uber's visualization team. People in my team have diverse backgrounds, some in visualization research, some in computer graphics, some in human-computer interaction. I myself studied architecture and urban design. It is my lifetime passion to understand how cities operate and how individuals make decisions inside a built environment. One of the many reasons DataVis excites me is how data allow me to look at the world in a way that's fundamentally different from my mortal eyes. There are visual wonders. By simply showing the hundreds of thousands of people moving around the city of London in Uber rides, you see the naturally formed fabric of the city, where the activities are, and how the pulse of city life shifts throughout the day. There are hidden stories. By running a little simulation to the question, what if everyone traveled in their own separate cars? We see the amount of traffic volume that's removed from the city streets by Uber pool matching riders with each other. At the end of the day, making pretty videos is probably the least significant part of our jobs. There are only so much assets you can craft out by hand. So instead, we choose to build tools that empower other people to also see through the lens of data and tell their own stories. We build tools for operators and engineers to monitor the performance of our marketplace in real time. We build tools for maps, policy, and data science to explore geospatial data interactively. And we build tools for machine learning engineers to debug their algorithms and identify patterns so they can improve our price and time estimation and detect fraud. All of these tools are essential to the business in every possible way simply because the sheer amount of data we're dealing with in our day-to-day jobs is not comprehensible without visualization. About a year and a half ago, my team partnered with the Advanced Technologies Group, also known as the self-driving car division of Uber, to help shape the future of driverless transportation. Today, I'm going to show you the web-based platform that we built for engineers and operators across ATG, from Pittsburgh to San Francisco to here in Bangalore, to quickly inspect, debug, and explore information collected in online and offline testing. Our self-driving cars and trucks are equipped with a suite of cameras and sensors. On the road, these sensors see way more than human drivers do and are capable of making decisions many times a second. For human engineers to understand why the self-driving car behaves a certain way, they need to first understand the context within which these decisions were made. What makes this product so challenging comparing to my previous DataVis projects starts with how much data there is to show on one screen. Let's break this view down. Drilling down from the top level, we first have the city context, or the base map. That includes the road network that connects the origin to the destination, the buildings, the addresses, the ground imageries. All of these are essential for a human user to orient themselves inside a built environment. On top of that, we have the autonomous vehicle maps. These maps contain every meticulous detail of the road. For example, where are the lane boundaries? Is it a bus-only lane? Is it a turn-only lane? What's the speed limit? Are there any street signs? What traffic light controls this lane, and where is it located? All of these data represents what the car knows about the road conditions and restrictions prior to the trip. And on top of all the maps, we have the vehicle log, which is all the information the car collects during operation. In this video, you see the autonomous vehicle driving through an intersection. Aside from the car itself, you also see the video feed from the front-facing camera and also all the other players on the road, the cars and pedestrians. You might have noticed that although we draw all the lane features in a more or less realistic fashion, we also developed an abstract visual language for vehicle logs. That is because the vehicle logs are 2 dimensions more complex than maps. They describe not only the features of space, but also time and probability. There are 3 critical stages of algorithms run based on sensor data. First, we have perception, which is what the car measures. For example, what objects are around us? Are they cars, bikes, or pedestrians? How fast are they moving? We use color coding to show the classification of the objects on the road, and that applies to both point cloud and bounding boxes. At times, if we are serving visualization to perception engineers, they would want to see the alternative shapes considered by the algorithm, so each object may have multiple bounding boxes. And for that, we use a slight variation of this palette. Second, we have prediction, which is what the car forecasts. For example, is that car going to turn in front of us? Where will that pedestrian be 10 seconds from now? Note that predictions naturally describe possibilities of the future. They do not exist in the physical world yet, and they may change at any time given new information. Now that becomes an interesting data visualization design challenge. How do we show things that are time slices from the future but only relevant to the present? For prediction, we draw paths out of every object on the road that are the projected trajectories. Along each path, we use a dot to signal where that object is expected to be every 0.1 seconds into the future. Now, just by looking at the density of the dots, you are able to tell how fast that object is moving, and also is it accelerating or decelerating. Similarly, each object may have multiple predicted trajectories if the engineer cares about the alternatives considered by the algorithm. Last, we have planning, which is what the car decides to do. For example, are we changing lanes to pass this car in front of us, or are we stopping behind it for this light? These are all decisions that eventually go into the car pressing the pedal or turning the wheel. Similar to prediction, we draw a wide green path out of the car to show the planned trajectory of the car. And along that path, a dot for every 0.1 second showing where the car expects itself to be in the future. If the engineer wants to see whether an object is going to get too close to the planned trajectory, we have something called the look-ahead capsules. It works like this. They will specify a time, say 5 seconds from now. Now, every object will have a ghost version of themselves showing where they're expected to be. Sometimes, if we're dealing with simulations, we also want to see what the car could have done given different circumstances. And for that, we draw a second car on top of the log in translucent colors. Before I dive into how we implemented the above design, I'd like to take a moment and talk about why we chose the web as the place to build this platform. Prior to this investment, ATG had a generic purpose visualization tool that was an ad hoc desktop software. That tool loaded maps and logs from files on a disk array, therefore only works within one office. It only runs on a particular build of Linux, on a particular configuration of hardware. And because of all the plugins people wrote all over the years, it takes minutes to start up. The tool served the team well throughout its early prototyping years, but like every organically organized software project, eventually failed to scale. Some advantages of the web are obvious. The web is hardware agnostic. Anyone can use this tool on any operating system from anywhere. And to share a log across systems is as easy as copy and pasting an URL. This would remove the previously existing OS hurdle in the organization's tooling and also open the gate of scaling this team beyond the city of Pittsburgh. We also value fast cycle of iteration. With the web, we will be able to develop and deploy incrementally. And for the user, that means to get the latest version of the software, they can simply refresh the web page versus downloading and installing a new app. Also very important to this project is customization. Each team at ATG would have their own needs to tailor their own data visualization types and user experience. HTML5 and JavaScript is a tested and true system for quickly putting together complex and powerful UI systems. It also enables us to hook up with the existing web-based tools such as task management systems. Still, when we first proposed to build this platform on the web, many people were skeptical. The strongest concern at the time was whether the browser could support the performance that they needed to render millions of data points at high frame rate. To understand the amount of computation involved, let me use the data coordinates as an example. It introduces a lot of complexity when you put all the data from different sources together, because humans and autonomous vehicles consume data in different coordinates. The base map is longitude and latitude. The autonomous vehicle map is divided into chunks we call submap. Each submap covers roughly the size of an intersection. Each submap has its own position and orientation. And every lane feature is measured in meter offsets inside that submap's coordinate system. And on top of that, everything in the vehicle log is measured in relative position and orientation from the original pose of the car. Now, when you pull all those data together, just to match them together in one 3D scene takes a lot of transformation. The rapid evolution of the web has been challenging every notion we have about what's possible in a browser. Did we lose it? Okay. In our case, WebGL grants us access to the power of the GPU. While the CPU can execute instructions at a higher speed, the GPU can perform repetitive jobs magnitudes faster by running them in parallel. Over the past 3 years, engineers in my team have been building a web-based visualization tech stack from the ground up. We have ReactVis and ReactMapGL, which adapts popular frameworks such as D3.js and Mapbox.gl into the reactive programming model. We have LumaGL and Deck.gl, which utilize WebGL to power large-scale visualizations. If you think of data visualization as the transformation of data from its bits representation to its pixel representation, then dealing with a large amount of data points is essentially repeating the same transformation over and over again, and the GPU is precisely designed to do that. Deck.gl offers shader modules that perform common visualization transformations on the GPU, for example, the Mercator projection. In this demo, you see Deck.gl rendering almost 1 million data points, a scatter plot, at 60 frames per second. Every time the user interacts with the map, the CPU is not dealing with the repositioning of any of the dots. Instead, it recalculates the map center and zoom level and sends that to the GPU. That's the only way we can get this type of performance. Deck.gl can also perform data filtering on the fly. In this demo, we are restyling 320,000 arcs based on mouse position. Again, the CPU is only sending the X and Y position of the pointer to the GPU, and the GPU is doing all the heavy lifting of figuring out which arcs to draw and which arcs to hide. Just last week, we announced Deck.gl version 6.0. In this release, we utilize the WebGL 2 standard that's already implemented in Chrome and Firefox to offer even more powerful GPU processing. In this demo of the highway safety in the United States, every road segment is colored by fatalities per mile. And whenever the user interacts with the year slider, the GPU is smoothly interpolating between two sets of over 400,000 vertex colors. In this demo, the GPU is aggregating 4.5 million data points. Every time the user zooms or pans around, it recounts the number of points that falls into any of the tens of thousands of grid cells on screen. Deck.gl's core concept is layers. Think of each layer as a packaged transformation from a given data set to a common visual representation. By compositing multiple layers in a shared 3D context, developers can quickly put together very visually complex and appealing visualizations. Out of the box, Deck.gl offers layers that are the basic building blocks for every visualization, including the icon layer, the scatterplot layer, the GeoJSON layer, the hexagon layer. You can find many more interactive demos and their source code on our GitHub pages. Now, in this video, you really start to see how point cloud layer, mesh layer, path layer, and polygon layers come together in action. This 15-second log snippet loads over 100 megs of compressed geospatial data from multiple service endpoints. They are rendered in over 80 Deck.gl layers, and each layer has its own coordinate system, projection method, and styling logic. All the layers share one single camera that represents the user's point of view. During a playback, every position and color is refreshed 10 times a second, and Deck.gl is optimized to handle this extremely efficiently. As a fast-evolving technology, autonomous vehicles never cease to produce new metrics and new techniques. Each team at ATG has their unique visualization needs. We are a tiny team of engineers, yet we aim to support hundreds of engineers across ATG for their ever-changing use cases. To do this, first, Deck.gl's layer-based approach to visualization allow us to create custom profiles of data streams that we can turn off and on demand. We also created a protocol that streams generic 3D data. Streaming allows us to break the memory limit of the browser so that we can play a log that is 1 hour long or even infinitely in real time. This protocol we developed in-house also allow the backend to specify the visual properties of the geometries alongside with the data so that the front end would receive a previously unknown data stream and immediately understand how to best render it. The protocol also supports specifying the accompanying UI to the data, for example, charts or tables. This allows teams to just plug in their own data stream and immediately control the experience without having to redeploy the front end. Lastly, we package this the visualization platform and publish it internally as a reusable React component so that every engineering team in ATG can build their own web applications around this core 3D renderer. Having multiple web services developed sharing the same core avoids creating one mammoth application that does everything and everything slowly. Instead, in our current workflow, multiple teams collaborate on the shared code base and work independently in their dedicated UI so that they don't interfere with each other in terms of deployment or performance. This is an example app that we built on the platform to tackle the triage use case. Engineers and operators will need to go back to a certain point of time and look at what the car did and why it did it. If anything went wrong, maybe perception, prediction, or motion planning yielded the wrong result, or the car just failed to execute the commands. With this tool, users can drill down into any object in the 3D scene, see the context that occurred around it, how it behaved, how it interacted with others on the road. From there, they can attach comments, create tickets, pass this on to the responsible team for further investigation. This is an example tool we built on the platform for the debug use case. Autonomy engineers would run their software in simulation and then compare the result with a previous version of the software, see if there's any difference in performance. Using this tool, they can play two logs side by side or on top of each other so they can spot even the slightest change in the car's behavior. At Uber, we envision building a safer and more reliable future for transportation, and we cannot do that alone. From the visualization team standpoint, that means we want to empower the policymakers, the city planners, and the general public to understand their cities through the lens of data, just like we do. One of such initiatives is Uber Movement. Uber Movement is a data sharing platform that we built where we take the billions of Uber rides around the globe, anonymize them, extract insight, and share them back with the city where we operate in. The travel times dataset is currently available for dozens of cities, including Bangalore. With this tool, you can query the average time it takes to travel from point A to point B within the city. You can also filter that travel time by a date range, weekday, or time of day. You can also compare multiple time ranges to see if there's any change. Cities already use this data set to measure, for example, the impact of major road closure due to construction. Or they use it to compare the before and after of implementing a major traffic law, for example, plate number restrictions. This is the first time they can immediately get feedback for the decisions that they make. We are also actively working on sharing other data sets such as street speed or road safety. When you want to put the open data from Uber and other sources together, Deck.gl is our most powerful visualization platform on the web. The visualization team relies on open source projects heavily, and in return, we share almost everything we build back with the community. When I took this job, it was a huge sell that I am able to talk to the outside world what I'm doing and stay in touch with the database community. We're especially proud of the fact that every feature in Deck.gl is grounded in real-world scenarios, such as the autonomous vehicle platform. Everything we do in our open source frameworks are driven by and tested with the numerous internal projects that are heavy-duty and performance sensitive. If you are less comfortable with writing JavaScript, just this last April, we announced this open source project called Kepler.gl. Kepler.gl is a data analytics tool for anyone to create beautiful visualizations within a few clicks. In this video, the user just uploaded a CSV file of pickup and drop-off coordinates in the city of San Francisco, and now they are adding and tweaking a new visualization layer, all using a graphic user interface. Under the hood, Kepler.gl is powered by Deck.gl, and together they demonstrate the kind of feature-rich data visualization experience that is possible in the browser today. As we speak, my team is exploring open sourcing the tools we made for autonomous vehicle visualization. In this screencast, we show Deck.gl rendering an open dataset called Kitty. And the data is served with our own 3D data streaming protocol. We do not believe in reinventing the wheel behind closed doors. Together, we can get to the future a lot faster by collaboration and knowledge sharing. Although I only talked about the front-end piece of the platform, needless to say, a lot more effort went into this project to put all of these together. Aside from my visualization teammates, there are teams of engineers in Pittsburgh that are building the data infrastructure and services that ingest and make available all these data. We also have designers and researchers that work tirelessly with the autonomy engineers to understand what makes the best sense for them. And I also want to shout out a big thanks to the external community that have been giving feedback and contributing to our open source frameworks. That concludes my talk. If you're interested in the self-driving effort at Uber, go visit the ATG website, and I'm happy to take any of your questions regarding visualization. Thank you.